Hello everyone, I'm Alok Kataria and I have my co-presenter Hema Venkataramani with me. We both work in the core data part team at Nutanix, and today we are going to talk about the performance innovations which have helped constitute the new age hyperconverged stack for Nutanix. We'll look at how the basic tenets of system programming principles like minimizing context switches, avoiding TLB misses, or avoiding data copies have helped us evolve our stack. The way we plan to cover today's talk is to first give a quick overview of the Nutanix HCI architecture, after which we'll go through the nitty-gritties of the Nutanix storage data path and look at the optimizations we did at each of the layers. Lastly, we'll discuss some of the performance numbers we have collected, which showcase the benefit that we have got with all of these optimizations. So let's dive in. HCI in general makes use of commodity hardware with direct attached storage on each node and exposes a scalable and self-healing storage fabric over collection of these nodes. In this slide, you can see that we have n number of these nodes. Each node have its own CPU and memory as well as a direct attached storage. We have a hypervisor installed on each of these nodes, and we have a controller VM running on them. The controller VM is where we have the Nutanix software running. It is a distributed piece of software and is aware of every other node on the cluster. Using this distributed piece of software, we are able to provide a unified namespace across all the local as well as remote storage that is on this particular cluster. We call this as the distributed storage fabric. This enables us to provide features like VM storage, file storage, block storage, disaster recovery, data replication, and much more. There are a lot of things that differentiate the HCI stack, but I'd like to highlight the 4 key pillars of our design. Firstly, we have a flexible and fine-grained metadata design, which makes our system highly adaptive, scalable, and makes healing faster because we are dealing with a small chunk of memory of data at any point in time. Secondly, we maintain locality of data, which ensures that we get the best performance out by doing local reads as well as removes the dependence on the network. With respect to writes, we at Nutanix are paranoid about user data and ensure that every write that is done on the Nutanix stack is written to a remote node at the desired and configured replication factor. We never acknowledge a write back to the user unless the replica has been persisted. Adding a node to an existing cluster can be done without any downtime too. Work is equally divided amongst all these nodes, which ensures that we get a truly scalable architecture. Let's dive in and look at the storage data path on a single node. All the storage, local attached storage, be it SSD, HDDs, or NVMEs, if there was an NVMe controller on the node, is directly passed through to the controller VM. We have user VMs which are co-located on the same node that are running on the same hypervisor. Any user IO that is generated inside the user VM travels on this fast VM IO path to the controller VM, and the controller VM eventually writes it to the local media as well as communicates with the remote Stargate, a remote controller VM to replicate it on remote nodes. We have done a lot of optimizations on this VMIO path for our hypervisor, which is the Acropolis hypervisor. My co-presenter Hema will go over the details of the optimizations that we have done in this particular VMIO path. I'm going to focus on the optimizations that we did in the controller VM which writes to the actual storage media. So before we look at all the details of the optimizations, let's look at what motivated us to look at all these problems. So this chart is from Intel, which shows how the storage hardware landscape has been evolving over the years. About a decade ago, we had hard disks, which were much more prevalent, with a device latency in the range of milliseconds. In this era, any software that took about 50 to 100 microseconds That didn't make a big performance dent at all to the overall application latency. But moving on with SATA or NVMe SSDs, we now see device latencies in the range of 100 microseconds, as well as a lot more parallelism with respect to the number of IOPS it can handle. More recently with Optanes, which is based on the 3D crosspoint technology, NVMe latencies are in the range of tens of microseconds. These latencies are now in the similar order of magnitude of some of the software overheads, like those because of a system call or context switches or data copies that happen between these boundaries. So this evolution of the hardware helped us, motivated us to look at how we can make our stack much more leaner and get rid of all of these software overheads. With that in mind, we took a look at the controller VM storage path to see the cost of the software from the point it enters the controller VM to the point it is actually read or written to the device. The controller VM is a Linux virtual machine, and the core data path service, which we call as Stargate, is running as a user application in this controller VM. All the devices are directly managed by the Linux operating system. Stargate uses an in-kernel file system to figure out where to write this data. And then it makes system calls to the block subsystem of the Linux kernel to write to the actual storage media. So you can see that there are two classes of system calls that are involved here, one through the file system and one to the actual block layer to do the actual read or write. Because the syscalls are expensive, we would like to get rid of these. For this to work, we took a look at the Blockstore project. Blockstore brings the complete file system handling in the purview of user space in Stargate itself. With Blockstore, we have redefined the data format so that we can manage the file system metadata completely in user space without any help from the kernel. This gives us control on the data layout on the disks, which enables us to do the second optimization, that is SPDK. Intel developed the Storage Performance Development Kit, which is an API which allows us to do I/O to an NVMe directly from user space. With the combination of both Blockstore and SPDK, we have managed to get rid of any context switches, or we have gotten rid of the kernel completely in the data path in the controller VM, making our software a lot more leaner. SPDK in itself is capable of saturating 8 NVMEs from a single CPU core. So that allows us to add as many local storage media on the particular device and not be bottlenecked because of the user space components. On this slide, we'll go through the design principles of SPDK, which provides all the benefits that we have been seeing, as well as we'll discuss the challenges that we faced while productizing the SPDK support. SPDK in itself is a collection of a set of building blocks which enables us to write highly efficient storage applications. In our stack, we use just the NVMe PCIe driver which is the user space driver for SPDK. SPDK interacts with the UIO or the VFIO in kernel driver for some of the basic admin activities. And one of them allows us to map the PCI bar of the device directly in the user space application. This ensures that we can do MMIO to the device directly from the user space. Secondly, SPDK also enables us to do DMA from user space. For this, it makes use of huge pages to ensure that the virtual to physical translations of the memory are always pinned in memory while the DMA transfer is happening. We have gone a step ahead and made changes both to our stack as well as to SPDK to ensure that all of the memory of Stargate is backed by huge pages and is now DMable, and SPDK recognizes that as DMable memory as well. Making use of huge pages for Stargate also got us another benefit, which is the better TLB utilization. With both of these things combined, we are now able to do MMIO and DMA directly from user space within Stargate without needing any data copies, uh, essentially. The second aspect of SPDK is that it provides lockless implementation, wherein all the NVMe hardware queues can be directly exposed to per Stargate application thread, and which allows us to do direct submissions of NVMe requests on the NVMe hardware queues without the need of taking any locks from any of the threads. SPDK also makes use of a polling mode, polled mode driver design, which avoids the costly two-way context switches that happen due to interrupt-based model in the kernel drivers. Polled mode driver design is, in our integration of this polling mode, we have done a few more optimizations wherein the polling is much more adaptive on our stack. We scale down the polar thread if the system is fairly idle, as well as scale it back up and do aggressive polling when there are a lot of outstanding IOs. A combination of all these aspects have helped us make use SPDK to its fullest potential in our stack. One of the biggest challenges with SPDK for productization was the manageability of SPDK disks. And the reason it is challenging is because since there is no kernel driver or block device driver that is driving the disks anymore, we don't have any of these /dev/NVMe devices under the devfs. This breaks a lot of user space tools, and NVMe CLI is one of the notable ones. NVMe CLI relies on doing IO cutters to the devfs nodes to get information like serial number of a disk or health information about disk. To handle this, we worked with Intel to expose character user space devices using the queues layer in the Linux kernel. Doing this ensured that now, whenever an IO cutter is done on a queues device, SPDK would get notified or would be able to handle that IO cutter in user space itself. IOStat is another tool that is used for collecting disk statistics, and this relies on getting the disk stats from the proc file system, which is again kernel managed. Since SPDK disks are completely managed in user space, the kernel has no knowledge or has no stats information about these disks. The way we handle this is we use the fuse layer in the Linux kernel to expose stats files, which are now backed by Stargate code. We modified IOStat to work with this new location of stats file for SPDK devices as well. So combined with all these changes, we have been able to provide the best performance for SPDK without losing on any of the supportability aspects of these pre-existing ecosystem of tools that is there on Linux. So let's move on to look at how we have embraced RDMA in our Nutanix stack. And I'll hand it over to Hema to talk about that.
Thanks, Alok. Hi, everyone. I'm Hema Venkatramani. I work in the core data path team at Nutanix. So far, we saw the overall Nutanix architecture and the impact of the Blockstore project with SPDK to optimize the storage path of the Nutanix stack. Next, we will see the improvements done to accelerate the network path in the Nutanix stack. To leverage this, we use RDMA. RDMA, or Remote Direct Memory Access, is a technology that allows data transfer over network by bypassing memory copies and context switches in the fast path. This proves very useful for latency-sensitive applications that would otherwise rely on the TCP stack. TCP stack resides in the kernel, and hence we would have to pay the penalty of performing additional memory copies to and from user space, context switches, and hence costly system calls to use a TCP stack. What RDMA allows applications to do is to leverage true zero copy of its buffers for network transfer. It also avoids using system CPU from doing all memory transfer work for the network path. Instead, it uses the NIX processor for performing the DMA operations. This saves enough system CPU for the rest of the software stack for its processing. RDMA is supported on top of the three protocols: InfiniBand, RoCE or RDMA over Converged Ethernet, and iVAR. For Nutanix, we use RoCE cards for leveraging the RDMA feature. Let us see how we have enabled RDMA in our stack. Firstly, on the configuration side, we have provided pass-through of the RDMA NIC to the controller VM. It also required us to connect the RDMA NIC to switches that support data center bridging. Data center bridging allows to receive congestion notifications and hence supports the RDMA NICs to perform appropriate flow controlling of the packets. Secondly, on the software side, we use the OFED libraries. OFED or Open Fabrics Enterprise Distribution is a set of libraries that are available for applications to set up RDMA connections and perform data transfers. The two main libraries are libIBverbs and libRDMA-CM towards this. We have also supported registration of memory regions in the Stargate process address space for performing the DMA transfer over the RDMA NIC. We have also supported polling of network completions to optimize the CPU cost, as otherwise we would be incurring system calls to determine the completion of data transfers. Next, let us see where RDMA is utilized in the Nutanix path. Leveraging network transfer itself is done at two parts in the Nutanix stack. First, it is used in the shipping of I/O requests and any accompanying data from the user VMs to the controller VMs. This we saw when we briefly touched upon the Nutanix architecture earlier. Secondly, we also use it in the replication of the data for a write I/O between two controller VMs for data availability and resiliency. For Nutanix, RDMA technology would benefit in both these paths which use the network. Now let's take a look at the replication of the write I/O and how it can use RDMA. As you could see in the picture, Stargate, when it processes a write I/O, first persists the data on the disk on the primary node. It then shifts the I/O via the network stack, which is TCP in the traditional Nutanix stack, to ship the I/O to peer Stargates. The peer Stargates also does similar processing, and after it persists the data on their disks, it sends the acknowledgement back via the TCP stack to the primary Stargate. Stargate will then acknowledge the I/O to the user VMs. As you could see, the traditional stack incurs the in-kernel implementation and requires the memory copies and context switches. To make it highly optimized, we have leveraged RDMA, where Stargate will be able to perform DMA directly into the peer's memory. This has highly shortened the write path, and it has helped us improve the performance of end-user applications like SAP HANA, Kafka, and big data applications. Next, let's see how RDMA is used in the shipping of I/O requests from the user VM to the controller VM and in sending the response back to the user VM. Before we look at that, let's take a look at the storage data path in today's Nutanix stack. As you could see, this path involves the user VMs, the hypervisor, and the controller VM. The I/O originates from the user VMs and is forwarded by the hypervisor to the Stargate process, which resides in the controller VM. The Stargate process then processes this I/O request, and once that is complete, it sends the response back to the hypervisor, which is then acknowledged to the user VM. The picture here specifically represents our Acropolis hypervisor, which is a KVM-based hypervisor. Now, in KVM-based hypervisors, we have KEMU or Quick Emulator, which is used to emulate the various resources like CPU, memory, I/O devices, display adapters, timers, etc. to guest virtual machines. If we simply implemented the Virtio spec data plane in KEMU, we'd have a context switch for almost every packet going from the kernel to the guest and vice versa. This is an expensive operation that adds latency to the stack. Also, modern OSs offer a multi-queue block layer. Each device has a request queue per CPU. This has the advantage that the data path within the guest OSs is completely lock-free and also allows them to generate large outstanding I/O. But the KMOS IO handling resides in a tight loop within a single thread, which does not allow the processing to scale at the rate that the IO is generated from the guest OS. To solve this problem, we use the vhost protocol, which enables us to implement a data plane going directly from the kernel that is on the host side to the guest by bypassing the KMO process. Towards this, we have implemented our own custom vhost user SCSI PCI controller implementation called Frodo, which sits outside of KMO on the host and handles all IOs from the guest's VirtIO controller onwards. The Frodo daemon running on the host has information about which VM disks are to be exposed for a specific VM. KMO process for that VM simply hooks up to this daemon and exposes this hook as a VirtIO SCSI controller inside the guest. Essentially, from inside the guest, one sees absolutely no difference between Frodo and a vanilla VirtIO SCSI PCI controller exposed by KMO. Frodo daemon is a much lighter than KMO and allows us to expose multiple queue, which are hardware queues, to the guests. It also reduces the latency by polling and optimizes the communication with Stargate by using the iSCSI protocol. It also allows us to load balance the communication across different Stargate processes. Now let us take a look where we can leverage RDMA in this stack. As you could see, the network component here is the usage of the iSCSI stack, which ships the IOs of the UVMs to the Stargate process in the controller VM, even if it is on the same host. As you could see, the traditional stack leveraging iSCSI, represented by the blue lines here, ships the IO from Frodo to Stargate. Here, we have leveraged RDMA by using the iSER protocol, which is iSCSI extensions over RDMA, to ship the IO from Frodo's memory space to the Stargate's memory space. This accelerates the communication by enabling zero-copy DMA operations and avoiding context switches. Now, let's take a look at the overall improvements we have seen so far in this presentation. Firstly, on the left side, we see the traditional stack. We have the guests that generate the IOs, which are later shipped by the hypervisor to the controller VMs. Stargate, listening for the incoming packets over the TCP channel, receive the packets and process them, which uses the in-kernel implementation, which is the file system and the block layer, for the storage stack. And later, for writes, it are shipped to the peer Stargates using the TCP path. The peer Stargates process similarly using the traditional in-kernel implementations, and once that is complete, sends a response back via TCP path to the primary node, which then acknowledges it to the hypervisor, which then percolates the same to the user VMs. As you could see, there are multiple bottleneck points that are using the in-kernel implementations and incurring memory copies and context switches. Now, the highly optimized New Age stack uses iSER for shipping the IO from the user VMs to the controller VMs. Stargate, which uses RDMA to listen for these incoming packets, receives the same and uses Blockstore and SPDK to process the storage path of the stack. For writes, these are again replicated over RDMA path to peer Stargates. Peer Stargates also use the same for persisting or reading the data from the NVMe devices by using the lean path SPDK stack. And once that is complete, they acknowledge the primary Stargate via RDMA path, which is then sent as an iSER response back to the AHV hypervisor, which is then acknowledged to the UVM. Now, what is the performance resulting from this new Age HCI stack? Let's take a look at that. I will now hand over to Alok to go over the performance numbers. Thank you.
Thanks, Hema. Now let's look at the performance improvement that we have got with all these changes. On this first slide, I'm going to talk about the improvements we have got with the changes that were done in the CVM or the controller VM. So essentially, that entails the changes, the improvements we got because of Blockstore, SPDK, and the RDMA-based replication code path. This chart shows, on the right-hand side, it shows the physical as well as the CVM configuration all those workloads were run inside a CentOS 8 UVM, which had 6 vDisks which were exposed from our data storage fabric. On the physical side, we had 8 P4510 NVMEs that were attached to each of the nodes. We ran a classic four corners benchmark that compares the sequential read, sequential write, random read, and random write performance. For sequential workloads, we are looking at the bandwidth numbers, which are in gigabytes per second. And for random workloads, we are looking at the IOPS improvements. In this graph, we are comparing three different configurations. One is where Nutanix stack is using the kernel file system with TCP/IP for the replication. Second is we use both the Blockstore as well as SPDK improvements, but still using the TCP/IP stack for replication. And the third is all the changes in the CVM, which are Blockstore, SPDK, as well as RDMA for the replication needs. Let's look at the sequential read numbers first. We see about like the sequential read is being done at a 1 megabyte block granularity. We see about 10% of improvement with SPDK and Blockstore combined. And the improvement is still modest because you would notice that with a 1 MB write, the amount of context switches that are happening is still limited because we are now doing much more work per context switch. So the 10% improvement is justifiable over here. You would also notice that RDMA doesn't have any doesn't make any difference on the read workloads, and that is because on the read side we are doing a read from the local media. Like RDMA only comes into picture when we are replicating it over to the remote node. On the sequential write, you would see similar numbers wherein even though we got better local writes with SPDK and Blockstore combined, the overall improvement was still 2%. And that is because this is still using the TCP/IP layer for the replication path. And as I had told earlier, we don't acknowledge a write back to the user unless the replica has been persisted. So the overhead that the TCP/IP brings on the replication path overshadows all the improvements that we have got with optimizing the local write part to the device. Though with RDMA, wherein we are able to get rid of the context switches on the replication path as well, we see that we get a combined improvement of about 20% compared to the kernel file system implementation, which used TCP/IP. Similarly, for the random read and the random write workload, the random workloads are happening at a granularity of 4K block. And we see over here that we get about 27% improvement with Blockstore and SPDK. And this is because with a 4K chunk granularity, we have a lot more IO operations that are being done. And the CPU is busy enough doing control side work, control plane work on every IO. With the help of Blockstore and SPDK, we have freed up the CPU to handle a lot more IOs, and that is what translates into the 27% improvement. Similarly, for random write, we see that the IOPS increase by about 24% combined when we have Blockstore, SPDK, and the optimized replication code path with RDMA. So what this graph shows, essentially to summarize, is that with all the changes in CVM, we are able to get about 25% odd improvement on all the workloads across the different block sizes. Moving on, let's add iSER to the mix and see what it brings to the table. So just to summarize, iSER optimizes the UVM to CVM code path when it provides the fast path over our Acropolis hypervisor. So what this graph shows is, so again, before we get into the graphs, we have one notable difference on the hardware front is that we now also have a 25 GB Mellanox CX4 card, which we'll use for the iSER implementation. Over here, I'm comparing just two configurations. One is the kernel file system, which was using iSCSI for the UVM to CVM or Frodo to CVM path. And the second configuration is Blockstore plus SPDK with iSER for the UVM to CVM code path. Over here, I'm just running the random read workload, and I've shown improvements with the IOPS that the application sees. And we see improvement of about 50 odd percent across the board. From the previous slide, you would notice that about 25 or 27% could be attributed to SPDK and Blockstore combined. So with iSER itself, we are getting close to 25% improvement on top of that. You would also notice that the improvement improves with increasing block sizes. And that is because with RDMA, we are also removing a mem copy that is being done for every IO. With bigger block sizes, that mem copy is going to show up a lot more on the iSCSI code path. And that's why the improvement is more pronounced with bigger uh, payload sizes. So just to summarize, with all the changes so before which I summarize, one thing that I would like to note is because I haven't shown any improvements of the right path over here. And that is because we are still working on integrating the iSER and the RDMA code path. Though notice that all the improvements that iSER gets is going to be across all the workloads, because the UVM to CVM path stays constant for all of these workloads. And these benefits are going to show up in all those benchmarks as well. So just to summarize, the new age hyperconverged stack, which does everything in user space, gets considerable or remarkable performance improvement compared to the traditional stack. And that's what we wanted to talk about. We can take any questions that you might have now. Thank you.